So there was a question about the last exam problem because the capacitor scheme might have been confusing to some folks. So I just wanted to talk about that real quick. Also, if there are other questions or concerns about the exam, like Jordan pointed out that, and I need to double check this. Jordan, which problem was that you were talking about? Sorry.
Problem one.
Yeah. So problem one on section two, it might be that the distance that the deflection you're getting is larger than the gap. So I'll need to go through and tweak some numbers there to make that not happen. I've tried to make the springs mass really small so that you could neglect them. And in doing so, I made it way too soft so that you can actually deflect it more than it's possible to do. So need to revisit that real quick. For the radius of curvature equation, that I gave you guys, the second term in the denominator is also supposed to be squared. Apparently, I just missed the squared in it. So anyway, but to answer Alexia's question specifically, so essentially you've got a situation that looks something like this. You've got your bias voltage. Don't remember if it's DC or AC. Don't particularly care at the moment either. But it's going to have one capacitor up here. I'm just going to call this CW1, a capacitor down here, that's CW2, and then you're taking your output voltage here at this node. This capacitance is getting larger as if it experiences an acceleration in the up the page direction. So that one's going to look like EA over D minus X. I'm just doing this very loosely. That's not going to be the actual capacitance because it's a capacitive comb drive structure, but it's going to be related to that, right? So we should see that that capacitance is getting larger. This one down here is going to wind up getting smaller because those fingers are moving further apart. Anyway, so that's not particularly important. Just want to make sure that you guys know what's going on. So for voltage division with capacitors, if we use the S domain impedance, so that's going to look like 1 over S CW1, and this is 1 over S CW2, then our voltage division relationship is going to look like V out is equal to V bias times, so I would have 1 over S CW2, 1 over S CW1, plus 1 over S CW2, multiplying through by CW1. So let's do it this way. Sorry, that should be a 2 there. So I'm going to multiply this guy by SCW2 over SCW2. I'm going to multiply the other guy by SCW1 over SCW1. And while I'm at it, I'm going to go ahead and multiply this guy up top by SCW1 over SCW1 so that I have a common denominator of S squared CW1 times CW2 so that this guy cancels this, and all we're left with is V bias times SCW1 over S times CW1 plus CW2, and the S's cancel each other out. So it's just bias voltage times CW1 over CW1 plus CW2. Sorry, my penmanship got super shitty there at the end, but effectively it works exactly opposite like you would see in resistors because capacitors combine oppositely of resistors. So this is how you'll get your final output voltage type thing, just using voltage division. Is that what you were referring to? Okay. Okay. So
what question is this for?
The very last giant problem where you're trying to find the relationship between the change in capacitance and the output voltage or something like that. Like one of the last things as part of that long chain of stuff. Okay, so couple of things. I obviously need to go back through and double check some numbers and all of that kind of stuff on the exam because some of the things aren't working out how I would expect them to. So I will try to have that updated this evening. If you need more time to work on the test, you're welcome to have it. Obviously, I don't want to penalize you for my mistake. So, okay, so let's get back into things. So first, I want to definitively answer North's question about piezoelectric actuation and can you make a crystal shrink? And then we're going to talk about how that would work out for a stacked actuator, which I think is where some of the largest confusion was coming from on behalf of myself as well. Okay. So we were talking about, so let's just say that this is piezoelectric actuation continued. Okay. So towards the end of our last class meeting, we found a relationship that says for a longitudinal piezoelectric actuator. And I'm just going to throw together a very quick and simplistic picture over here so that we all know what I'm talking about. So for a longitudinal actuator like this, our field would be in the 3 direction. And our force would also be in the 3 direction like so, where I've got my simplistic little coordinate system here. This is the 3 direction, this is the 1 direction, and one of the critical dimensions of the device is specifically the height. Okay. And we derived an expression that effectively said that the change in height due to some applied voltage was going to be E33. So that was our piezoelectric coefficient in the 3 direction divided by our Young's modulus. And this was multiplied by our applied voltage, meaning essentially that if we apply a positive voltage, our delta H is positive, and if we apply a negative voltage, our delta H should be negative. And that will generally be true. However, there is a caveat to that, and I think this is where the confusion was coming from. So we need to remember that a piezoelectric material is in itself a polarized material, which has some charge asymmetry. So essentially, we need to make sure that our voltage, like the positive polarity terminal of our voltage is on the positive polarity terminal of the charge asymmetry of the crystal itself in order to generate that positive change in displacement. So the poling of the piezoelectric crystal is going to tell us which polarity of voltage is going to make it expand and which polarity of voltage is going to make it contract. That comes into play when we're dealing with those stacked actuators very specifically, right? So we had a quick thing where we had a stacked actuator. So let's just say for a stacked actuator, and I'll draw a quick picture. So that was something akin to this structure. I think the one that I drew the other day only had 3 piezo elements like so, and then there were 4 total electrodes that we had access to. So something like this. And then I had them wired in such a way that this guy was connected to a positive polarity terminal of a voltage, and this guy was also connected to the positive polarity terminal of our applied voltage. So here is our voltage V, like so. And then I had this guy right here connected to the negative polarity, and this guy right here connected to the negative polarity. And I said that the change in height for this stacked actuator system is just N, which is the number of piezo elements, or the number of actuators, times E33 over Young's modulus times our applied voltage. This will only be true if I'm smart enough to remember that I need to flip the piezo elements, like alternate them in their direction, right? So if I had all of them such that, so I'm just going to use this as a blue, indicate the polarity of the piezo element effectively with blue here. So if I had this guy plus minus, this guy plus minus, and this guy plus minus, meaning that they're poled in this specific way, the one in the middle would actually shrink. So in order to fix that, I need to actually flip it upside down, and now they're all going to expand when V is positive, and they're all going to contract collectively when the applied voltage is negative. So if I don't have that distinction to where I need to actually physically flip every other transducer over, I'm going to get cancellation of the changes in height. With them flipped over, now I'm forcing them to all expand at the same time. So I think that should resolve the confusion there. Okay. All right, my apologies for that. It was a fun-ish research project. Well, done in, 30 minutes on my phone this morning right after I woke up. All right, so now let's talk about transverse actuation. Okay. So I'm going to start by drawing a little picture again so that we remember what it is we're talking about. So I've got a piezo element here. There's my top electrode and my bottom electrode. This area right here is A1. This area up here is A3. So when I apply a voltage across the electrodes of this guy, I'm going to get a field still in the up direction. So that's script E3. But for a transverse actuator, I'm going to wind up getting a force in the one direction, like so. So I'm effectively growing the crystal out down that axis. Just for what it's worth, one critical figure of merit here is the length of the actuator. But as we'll see shortly, the height will also be important. Okay. So this is our system. We're applying some voltage across the terminals that I have in hot pink, and we are expecting a force to be generated in the one direction, where, just for shits and giggles, this is the 3 direction, and this is the 1 direction. Okay, so picture representing what's going on has been drawn. Now let's sort out the math. So for transverse actuation, we would have our stress T1 is equal to Young's modulus times our strain in the one direction minus E31, our transverse piezoelectric coefficient, times our field in the 3 direction. If we allow the material to deform freely, then T1 is equal to 0. So our stress is equal to 0. So for a freely deforming piezo element, we would see then that E times S1 is equal to E31 times electric field in the 3 direction. And we could reorganize this guy pretty easily and find that our strain S1 is E31 piezoelectric coefficient multiplied by our field in the 3 direction divided by our Young's modulus. Once again, our electric field is just our voltage over our height. So that would be E31 V over E times H. And for a uniform strain, we could say that our change in length, so let me write it out this way. So uniform strain would be just delta L over L, right? So from that, we could say then that our change in length is going to be E31 times L divided by EH times our applied voltage. So I'm going to put a little circle around something important here. So that L over H ratio means that in a transverse configuration, the amount of displacement we generate is not independent of geometry like we saw in the longitudinal configuration. So if we want to get a large displacement, we need to have a large L over H ratio. Okay. Our force for this particular type of piezo element is once again just going to be F piezo, and that is K, our spring constant, times X, our displacement. So this is still just another material that is being extended, right? So we would have E times, sorry, that should be equal, E times A1 over L. So that is our spring constant for stretching this material in the one direction, multiplied by our change in length, delta L. Well, delta L over L is just our uniform strain. So that is E A1 times S1. And if we substitute in our relationship for S1 from above, this comes out to be E31 A1 over H all times our applied voltage. So this is what our generated force looks like for a transverse piezoelectric actuator. Okay, so went through that fairly quickly. Anybody have any questions about the transverse actuator? Everything derived was very, very similar to how we did it on Monday. It's just now we're using that E31 piezoelectric coefficient because the displacement that we're generating is in the one direction caused by a field in the 3 direction. Okay, so I want to talk about thermal actuation today as well. This should be fairly quick because we spent a lot of time talking about thermal sensing, and this is going to be pretty similar in some things. Okay. So The first type of thermal actuator that I'm going to talk about here, and I'm literally just going to talk about it because we've already covered literally all of the math, would be a thermal bimorph actuator. So essentially, instead of using the deflection of that thermal bimorph to tell what temperature change happened, we could force a temperature change by passing a current through it and generate some amount of deflection, right? So essentially, if we had, I'm going to try to draw this as best I can, but let's think about a beam. And it's going to be anchored over here in some way, right? Actually, that looks like shit. I'll just do it not three-dimensional so that I can wrap my head around it too. How's that sound? So here is our beam. So this is material 1, and it's on bottom, okay? We could, if we were so inclined, integrate wires into the surface of this beam. And I'm drawing these as resistors because we are going to make sure that our wire that we're integrating here has sufficient resistance so that it heats up when we pass a current through it, right? If I were to then put a second material on top, so imagine that this guy in orange is literally sitting on the surface. So this is kind of a top view type thing. Side view might look something like this. When we pass current through those wires, we are going to have conduction between the wire that is deposited into material 1, generating heat, and that's also going to conduct heat into material 2, and it's going to cause both of those beams to deflect, and the deflection is going to be governed by the thermal bimorph principle that we talked about when we were dealing with thermal sensing. So it's literally just the exact same thing, except that we are intentionally causing the heat to happen so that we cause a deformation versus we are seeing ambient heat cause a deformation, and we're trying to quantify what that temperature difference is, okay? So this is one way of thermal actuation, and you already have all of the math and all of that kind of stuff for it from when we talked about that particular lecture. So let's go into something a little bit more interesting, I think, okay? So now let's talk about how we might have thermal actuation with a single material. So this is thermal bimorphs or bimetallic strips. Now we're going to talk about thermal actuation with a single material. So let's say that I have a simple structure again, okay? So I have a beam, and now I'm going to anchor it on both sides. Well, if I anchored it on one side and we heated it up, it would just extend in its direction that it's free to expand, right? Because of the coefficient of thermal expansion. Well, if I restrict it on both sides, what I'm going to find out is that I'm going to develop some strain. So if this is the X direction, then our strain in the X direction is just going to be alpha, our coefficient of thermal expansion, multiplied by our change in temperature. However, we're also going to have some strain caused by this material trying to expand. So that's going to be Txx over Young's modulus, and this net strain has to come out to be zero because the material isn't deforming, right? So it's trying to deform, it wants to deform, but if we bound it on both sides, we can't. So our stress in this particular configuration is just going to be negative E times our coefficient of thermal expansion times our change in temperature, and our force generated in the x direction is just going to be our cross-sectional area. Sorry, that should be an A, not a delta. Misread my thing. Multiplied by our stress. So this will be EA alpha delta T. Okay. So effectively, we're generating some force that's pushing on those anchors. Okay. We can generate a relatively large amount of force, but it's not really doing anything. So let's talk about now how we might exploit the system's geometry to actually get some reasonable output out of this thing, right? Because what benefit is it to us to be able to push on two walls that are surrounding us? We are not going to move them. So let's talk about how we can do something with it. So what if I had, instead of a straight beam, a chevron shape? So something like this. So let's say that I have an anchor here and an anchor over here, and I manufacture through probably surface micro machining something that looks like this. So this is a chevron actuator. And what we'll see is that choosing a shape like this is actually going to exploit the geometry so that very small changes in the lateral dimensions will be amplified into a positive vertical displacement. Okay. So let's define some things for this actuator. So let's say that this distance from here to here is L naught. That is our nominal length. This distance from here to here is Y naught. And then this distance from here to here is X. Okay. So our thermal stress, thermal strain, S sub L. So this is just our strain along the length is going to be alpha, our coefficient of thermal expansion, times our change in temperature. Nothing wild or crazy there. And assuming a uniform strain, then our change in length, delta L, is going to be just SL times our nominal length L naught, right? So this is how much it's going to want to deform. This is just effectively a beam in extension, okay? So we're going to throw some good old Pythagorean theorem at this thing and see if we can shake out what's going to happen here, okay? So I have a right triangle, effectively. So if this thing is expanding, then my hypotenuse is going to look like L naught plus delta L quantity squared is going to be equal to x squared plus y naught plus delta y quantity squared, where delta y is the change in the y direction that we're going to see, okay? So are we all okay from where this relationship came from? It's literally Pythagorean's theorem. A squared plus b squared equals the hypotenuse squared. Nothing wild or crazy there, okay? So let's expand this thing out. So we would have L naught squared plus I don't know where I got rid of a factor of 2 here, so I'll just do this out for legit. So twice delta, actually, let me do it twice L naught times delta L plus delta L squared is equal to x squared plus y naught squared plus twice y naught delta y plus delta y squared. So did I expand these polynomials out correctly? Let's start there. Don't know how I missed a factor of 2 in my original notes, but it is what it is. So couple of things. First, we are going to make an assumption here, and this should be a pretty easy assumption to make, that delta L squared is going to be very small. So that can effectively be neglected, right? So in order to get a large displacement out of this thing in extension, effectively, we would need to have a really long length. So the ratio of delta L, comparing the change in length to the nominal length, delta L is going to be very, very small. And I'm going to make the exact same assumption about delta Y. Since it's going to be small, I'm just going to neglect it for now. Now I'm going to figure out x squared here, okay? So we know that for our undeformed chevron system, I'll do this over here, we would have L naught squared is equal to x squared plus y naught squared, right? So rearranging, we could say that x squared is literally just L naught squared minus y naught squared. And so I'm just going to substitute that in because my x dimension literally never changes for this thing. So that's going to look like L naught squared plus twice L naught delta L is equal to L naught squared minus y naught squared plus y naught squared plus twice y naught delta y. Have I screwed up any algebra yet? Okay, so I've got an L naught squared on this side and I've got an L naught squared on that side, so they cancel each other out. I've got a minus y naught squared here and I've got a plus y naught squared here, so they cancel each other out. And so all I'm left with is twice L naught delta L is equal to twice y naught delta y. And I'll be damned if those 2's that I forgot originally don't even matter. Lucky for me. And we wind up finding that our change in displacement in the y direction is going to be approximately equal to L naught over y naught multiplied by our change in length. So effectively, our extension gets amplified by a factor of L naught over Y naught. So the steeper that we make our chevron, essentially, the more amplification of that scaling extension we are going to see. So we can actually generate relatively large displacements with a thermal actuator if we orient it to where when they push into each other, they generate an upward displacement as opposed to just a straight extension displacement. Okay. Two other ways that we could potentially have single material actuation. These aren't going to really involve any math because it's all dependent on the geometry. Is we could have asymmetric actuators. Do I need to wait to start this because you guys are still taking notes, or am I good to move along? Okay, well, the only person I see is giving me a thumbs up, so I'm just moving along.
Wait, so the bigger Y naught is, the smaller delta one will be?
Yeah, so I guess you need it to be less steep but non-zero. Do that. Hold on, let me check so L naught delta L. Yeah. So we would need a slight bend. So what Mr. Finch was asking was how to get large displacements out of this guy, because the change in Y is inversely proportional to Y naught. So effectively, the smaller Y naught is, the larger the displacement will be. I need to look into that. This math seems legit, but that doesn't seem intuitively correct.
Yeah.
So I'll make a note to look into that. Actually, no. So it does make sense. Sorry, because if you had them oriented like this, we are only going to see the longitudinal displacements effectively, which is the thing that's small because this is a spring in extension. So we need them like this to generate the larger thing because we have to have them pressing against each other enough to generate a large force to give us a displacement in the up direction.
Oh.
Yeah.
But just not zero.
Right, but not zero, because then it's just pushing into each other and you're generating no vertical displacement whatsoever.
But then at what point, like, it can't be very close to zero either, though. Like, at what point is this viable?
I don't know, man. I could look into the literature because chevron actuators are actually used fairly regularly. So I'd be interested to see if there has to have been some research done into optimizing these guys, because you do bring up a good point. If you only had an angle here of like 1 degree or something like that, like technically you've made a chevron actuator, but is it going to be of any use? I'd be willing to bet that it needs to be an appreciable value for Y naught, but larger than zero.
That one thing is just forced to go in a single direction. Since if you go a straight beam, then it could go in either direction. Once you force it slightly.
So that is definitely fair. So you're assuming that essentially if you generate enough force, it's going to, so that would be almost like bistable states, but you don't know which one it's going to assume. So it would just have a curved deflection and you don't really have any guarantee as to whether it's going to deflect up or down. This is forcing it in one particular direction. Yeah, okay, that's fair. Okay. Asymmetric actuators. This will be our last little miniature topic for today. So, there are two ways that are traditionally, or two methods that are traditionally used to generate asymmetric actuators. The first is to simply have a situation like this where we have two different legs of varying lengths. And we're just going to rely on the coefficient of thermal expansion here to generate our displacement. Okay. So, and I think I touched on this briefly a few minutes ago, but essentially the longer the leg is, or the longer the nominal length of the leg is, the more it is going to expand under a specific amount of applied heat, right? Because it is a relative change, okay? So if both of these legs are experiencing the same amount of heat, this guy that is longer is going to expand more, and it is going to cause a deflection in this direction. And then we can use that to press on things or whatever if we need to, right? So this is essentially saying that the longer leg will heat up more because its RTH is greater. So thermal resistance is greater than the short leg when current flows through the microstructure. A different methodology for having something like this would be to once again have two legs. Now the legs are going to have the same length, but they're going to have different cross-sectional areas. So we would have a hot leg and a cold leg, right? So this will be the hot leg. RTH is large. This will be the cold leg. RTH is small because it has more cross-sectional area, and the thermal resistance is related to cross-sectional area over length, right? So having a larger cross-sectional area gives us a lower overall resistance. And so what we would see is that we are going to be generating a displacement in the direction of the cold leg, because a hot leg heats up more and therefore expands more. So those are different ways of getting asymmetrical thermal actuators. So the hot leg singular, not like the Rod Stewart song, hot leg expands more because RTH is proportional to cross-sectional area, generating a displacement or deflection in the direction of the cold leg. All right. We're done for today. So we can go to the career fair if we want to.